Good evening everyone. I welcome you all to the problem solving session of the NPTEL course on thermodynamics, and I am Pradeev E. I am one of the TA for this course. Today I will solve the problems that were given in the week 3 assignment, and then I have some problems on work and heat transfers. So the first problem is, the first question is, which of the following properties are desirable for a thermometric fluid in a liquid in glass thermometer? More than one option could be right. So the first option is small coefficient of thermal expansion, second is large coefficient of thermal expansion. So when we have a liquid in gas thermometer, so it is like a mercury thermometer that we generally use, mercury or alcohol thermometer. So we have a glass tube, and on the bottom there is some bulb filled with the liquid, and then this is where we put the surface of which we have to measure the temperature, and then this and based on the temperature the fluid expands, and then that rises to this tube, and at some steady state it goes to some point, and then we have a graduation. Then based on the liquid level we say what the temperature is. So now if the coefficient of thermal expansion is very small, then that means for very high temperature rise the expansion will be low, the volumetric expansion will be low. Then what will happen, then we will say for 50 degrees Celsius we will be able to have only very small rise in the liquid level, so that is not desirable. For high resolution of the instrument we need to have very high thermal expansion, so that means even for 1 degree Celsius we can have very big change in volume, and so that can be seen as a very large variation in the liquid level. So in terms of coefficient of thermal expansion it should be very large. And second or the third and fourth is a low freezing point and high boiling point, or high freezing point and low boiling point. So since it is a liquid in glass thermometer, we want to have the substance, the fluid in liquid condition state for wide range of temperature. So that means it should be, the freezing point should be as low as possible and the boiling point should be as high as possible. So for water it is 0 degrees Celsius and to 100 degrees Celsius. So with water we can measure till between only 0 and 100 degrees Celsius. But if there is another liquid which can go up to minus 100 degrees Celsius and it will stay at liquid even at say 300 degrees Celsius, then that is more desirable than this, right? So that means low freezing point and high boiling point is desirable. And fifth and sixth is the thermal expansion of the liquid should have linear relationship with the temperature or the non-linear relationship. If the relationship is non-linear, then the graduation cannot be linear. So the graduation also should be non-linear. So generally for any instrument it is better to have linear graduations, and so that it is easy for the user to interpret. So it is the thermal expansion of the liquid should have a linear relationship with temperature is desirable. So these three are the options, desirable properties. Second question, which of the following values of temperature is or are designated as absolute zero? So here we know 0 Kelvin is absolute zero, and 0 degrees Celsius is not. 273.15 Kelvin is again 0 degrees Celsius, and this we know that it is 0 Kelvin. So option 2 and 3 are right answers. The third problem, consider two slabs of equal length, breadth and thickness made of two made of two different materials having thermal conductivities K1 and K2. The rates of heat transfer through the two slabs in x direction as shown are the same and is equal to Q dot. If all other conditions are the same and the slabs are having temperatures T1, T2, T3 and T4 as shown, and T3 is greater than T1, that means T3 is greater than T1, and this is further greater than T2, and T2 is greater than T1. So it is like first T3 in the temperature scale, then T1, and then T2, and then T4. So this is the minimum most point, and T3 is the maximum most point, and then T1 and T2 lies somewhere in between these region. Choose the most appropriate option. So the only that material of the two slabs are different, so having a thermal conductivity of K1 and K2, whereas since they have given length, breadth and thickness are same, this x1 should be equal to x2, and they have also given Q dot is also same for both the conditions. Now intuitively we can say if there is a large thermal temperature difference for same heat transfer to occur, then that means there is more resistance in the heat path. So that means the thermal conductivity of the material is low. So that is K is lesser when compared to K1. So that means K1 is greater than K2. So option is 1. So if you want to do it mathematically or using the equation, we know Q is equal to Ka delta T by delta X. So it is said that both the Q are same, so that means K1 area delta T, or I can write for the one it is T1 minus T2 by delta 1x delta x1 is equal to K2A T3 minus T4 divided by delta x2. Here Ka is same area because slab has equal breadth, length, breadth and thickness, so delta x is also same. So we are left with only K1 into T1 minus T2 is equal to K2 T3 minus T4. So now these two quantities are equal, but we know T1 minus T2 is less than T3 minus T4. So if we have K1 by K2, this is equal to T3 minus T4 by T1 minus T2. So this we know the numerator is higher than the denominator, that means it is greater than 1. So that means K1 by K2 is greater than 1. So K1 is greater than K2. I hope this problem is clear. If you have any questions, you can ask now. Fourth question, choose the correct options according to the 0th law of thermodynamics. So the first option is if two or more thermodynamic systems are in thermal equilibrium with each other, then until they must be in thermal equilibrium, thermal, mechanical, chemical and phase with each other. Second is if two thermodynamic systems are each in thermal equilibrium with the third system, then all the three systems are in thermal equilibrium with each other. So option 2 is right, others are not. This problem is little large. Okay. So the fifth problem is thermometers A and B are calibrated at ice point and steam points. The relationship between the temperatures measured by A and B is TA is equal to K plus I into TB plus M into T square B, TB square, where K, I and M are constants, and TA and TB represent temperatures measured by the thermometers A and B in degrees Celsius. When thermometer A reads 41 degrees Celsius, thermometer B reads 30 degrees Celsius. When B reads 41 degrees Celsius, A would read dash degrees Celsius. So there are two thermometers A and B, and both has a relationship given by TA is equal to K plus I into TB plus M into TB square. These both thermometers are calibrated at ice point and steam point. So that means at ice point, TA is equal to 0 degrees Celsius, and since it is calibrated, that means both thermometers are showing the same value. So that means TA and TB are showing 0 degrees Celsius, and at steam point, TA and TB will show 100 degrees Celsius, and at the third point we have TA reading TA is equal to 41 degrees Celsius, while TB is showing 30 degrees Celsius. Now we can substitute all these three relation values in this expression, in the equation, and then we will get the we can find the values of K, I and M, and then we will be able to find the value of A when B reaches 41 degrees Celsius. Now put in the first value, TA is equal to 0 equal to TB, that will show TA equal to TB equal to 0 degrees Celsius means K is 0, right? Because we will have TA on the LHS we will have 0, and on the RHS right hand side, except for K, we know other terms will become 0, so K should be 0. Put in 100 for TA and TB, we will have 100 is equal to K plus 100 into I plus 100 square M. So now K, we know that it is 0. Now I can divide the expression by 100, and then I will have 1 is equal to I equal to 100M, sorry, plus 100M. So this I can take it as equation 2, and in the third case we have TA equal to 41 degrees Celsius and TB is 30 degrees Celsius. Solving, so putting this in the equation, we have 41 is equal to K plus 30 into I plus 30 square M. So this is K, we know K is 0, 41 is equal to 30 I plus 900 M. So this becomes equation 3. Now we can solve for equation 2 and 3 and find the values of M and I. I would write 3 minus 9 into second equation. On the right hand side we will eliminate M, and on the left hand side we will have 41 minus 9 is equal to we will have 30 minus 9 I. So this will say I is equal to 41 minus 9 is 32, and this is 21. So we have found the value of I. Substituting this in 2, we will have 1 is equal to 32 by 21 plus 100 m. Now we can calculate m as m is equal to 1 minus 32 by 21 whole by 100. So this is minus 5.238 into 10 power minus 3, and I would write the value of I also. This is 32 by 21. This is 1.523. Now I can write this equation. So we had TA is equal to K plus I into TB plus M into TB square. So this is K is 0. So I is 1.5238. 1.5238 TB minus 5.238 into 10 power minus 3 TB square. And now the value of B is 41. So TB is equal to 41 degrees Celsius, which implies TA is equal to 1.5238 into 41 minus 5.238 into 10 power minus 3 into 41 square. So this is 53.67 degrees Celsius. Do you have any questions with the problem? Okay. Excuse me. In the next problem, we have an engineer who proposed a new temperature scale in which the ice point of water is taken as 200 degree Q and the steam point is taken as 500 degree Q. So that means 0 degree Celsius is equal to 200 degree Q and 100 degree Celsius is equal to 500. What are the corresponding values in degree Celsius for 100 degree Q and 300 degree Q if the relationship between the two temperature scales is linear? So that if it is linear, we can write C or degree Celsius is equal to so for we will write y equal to mx plus c for linear line. Now we can have degree Celsius is equal to m into degree Q plus C constant. So or I would write C1. m1 qc1. Now substituting the first known value, when it is 0, it is 200 degree Q. 0 degree Celsius is 200 degree Q. We have C1, we will have C1 is equal to okay, alright, 0 is equal to m1 into Q. Q is 200 plus C1. So C1 plus 200 m1 is equal to 0. Okay, this is one expression, and then from this relation we will have 100 is equal to 500 m1 plus C1. So this is one expression. You can write this as 1, this as 2. 2 minus 1, C1 will get cancelled, then we will have 500 minus 200 of m1 is equal to 100. So m1 is equal to 100 by 300. So this is 1 by 3. M value is 1 by 3. And then we can find the value of C1, substituting this m1 in equation 1. We have C1 plus 200 by 3 is equal to 0. So C1 is equal to minus 200 by 3. Then we can also cross verify if this thing satisfies. When it is 0 degree Celsius, we have you can put in this equation and find. So at 0 degree Celsius we have 200 as Q. So m1 is 1 by 3. So 200 by 3 minus 200 by 3 will get cancelled. At 100 degree Celsius we will have 500 Q. So 500 by 3. On the right hand side we will have 500 by 3 minus 200 by 3. So this is 100 by 300 by 3, and that is 100. Yeah, so it is matching. Now we want to find the temperature in degree Celsius when the Q in the new temperature scale it is 100 degree Q. So we can substitute here directly. So now I can also rewrite this equation using the value. So C is equal to Q by 3 minus 100 by 3, or I can write Q minus 100 by 3. When for sixth problem we have Q is equal to 100 degree Q. So then C is equal to 100 minus 100 by 3. So this is 0 degree Celsius. For the seventh problem, we can write 0 degree Celsius. For the seventh problem, sorry, it is minus 200. So Q minus 200 by 3. So then it becomes minus 33.3. So this is 100 minus 200 by 3. So it will become minus 33.3 degrees Celsius. And similarly, for the next problem we have 300 degree Q. So C is equal to 300 minus 200 by 3, and this is 33.33 degrees Celsius. So here it will be minus 33.3 degrees Celsius, and here positive 33.3 degrees Celsius. The next problem, we have a planar ball is which is 20 centimeters thick with an area of 2 meters square and has a thermal conductivity of 2 watt per meter per Kelvin. If the temperature difference between the two sides of the wall is 200 degrees Celsius, then the magnitude of rate of heat flow across the wall at steady state condition is dash watts. So we know Q is minus Ka delta T by delta X. Here K is given as 2, area is given as 2 meters square, and delta T is 200 degrees Celsius. 200 temperature difference in degree scale and Kelvin is also the same. So we have delta T as 200 and the thickness as 20 centimeters. So in SI units we will have it as 0.2 meters. So you can calculate the heat transfer in watts. And this is so it is 40 watts. Sorry, the answer is 4000. A circular disc of diameter 20 centimeter and thickness 5 centimeter is hanging from a ceiling of a room. If the ambient temperature inside the room is 20 degrees Celsius and the disc temperature is 75 degrees Celsius, then the rate of cooling due to convection is dash watts. Take heat transfer coefficient as 2 watt per meter square Kelvin. So heat transfer due to convection is HA delta T. Here H is given as 2. The temperature difference is also known. Delta T is equal to 75 and ambient of 20. So 75 minus 20 is 55 degrees Celsius. Now area is what we need to find. So since it is hanging from the ceiling, we can assume that all the surface are used for the heat transfer. So we can have area as the flat surface area flat plus the curved surface area. So area of flat surface is 2 into area of the square, so that is 2 pi d, and diameter is known as 20 centimeters, so that is 0.2 meters. So you can calculate the flat surface area, that is 1.256 meters square. Similarly, curved surface area is pi d into height or the thickness. So now pi is pi, and then diameter is 0.2, thickness is 0.05. So we have 0.0314 meter square. So curved surface area is almost negligible when compared to the flat surface area. Still we can calculate area as 1.256 plus 0.0314, that is 1.2874 meter square. So Q is 2 into 1.287 into delta T of 55. So this comes to be 141.6 watts. Yeah, so area of this is not right. Area of flat surface is pi by 4 d square. So we have two surfaces, so it is into 2. So then we will have pi by 4 into 0.2 square into 2. So this is 0.0628 meter square. So this comes to be around 10.36. Okay, we can move to the next question. We have to match the table. So the thermal conductivity of water, air, mercury and copper are given. The copper value should be 385. So D1 we have 3 options. Air should be the lowest, so B should be with 3. So this should be the option. So do you have any questions in the week 3 assignment problems? answer on questions, I will move on. In the problem we have a 1000 watt ion which is left on the ironing board with its base exposed to air at 20 degrees Celsius. The convection heat transfer coefficient between the base surface and the surrounding air is 35 watt per meter square degree Celsius. If the base has an emissivity of 0.6 and a surface area of 0.02 meter square, determine the temperature of the base of the ion. So we have two mode of heat transfer occurring from the base from the ion base. So, but the total heat is known as 1000 watts. So Q by convection and Q by radiation. Q by convection is HA delta T, whereas Q by radiation is emissivity into sigma T1 power 4 minus T2 power 4 is there something else for radiation? Okay, so we have sigma epsilon A sigma T1 power 4 minus T2 power 4. So now this total heat Q is equal to QC plus QR. Now area is given, H is given, so we can write this as 1000 is equal to QC is H is 35 into area is 0.02, sorry, 0.02 into delta T is this air in T air is 20 degrees Celsius and that would be 293 Kelvin. Now we can have this delta T as temperature of the base minus 293 Kelvin plus epsilon emissivity is 0.6 into again area is 0.02 into Stephen Boltzmann constant is 5.67 into 10 power minus 8 minus into TB power 4 minus T2 is 293 Kelvin, 293 square sorry, power 4. So this has to be solved iteratively, or you can also have some solve function in the scientific calculator. So this is 1000 into 0.7 TB minus 293 plus 0.6 into 0.02 into 6. So this is 6.804 into 10 power minus 10 into TB power 4 minus 293 power 4. this is okay. I was right. 143. Can you try to solve this? So I've got TPS 947 Kelvin. So this is by directly using the solve function in the scientific calculator. If you do not have, then you have to iteratively start with the initial guess. Say you can start with the initial guess of say TP has to be more than the air temperature, so you can say it is 500 Kelvin. Okay, and then calculate the value of Q on the right hand side. Then see if it is more than 1000 or less than 1000. If it is more than 1000, you have to come down, or if it is less than 1000, you have to go for a higher temperature. And then you can also solve like this. So now if you solve say for 500 Kelvin, I solve for 500 Kelvin. Now for 500 Kelvin I got the Q value as 182 watts. So then I know that I have to increase my Q or the temperature. So now I can say go for 700 Kelvin. Then Q values will be 443 watts. Now say I go for 1000 Kelvin. Then I will get 1170 watts. Now I know that it is between 700 and 1000 watts. Now I can find for 900 Kelvin. Then I will get Q as 866. So I know it is between 900 and 1000 Kelvin. So similarly you can iteratively find this value. Do you have any questions so far? Okay. In the next question we have a piston cylinder device. Initially contains a volume of nitrogen gas at 130 kilopascal and 120 degrees Celsius. The nitrogen is now expanded to a pressure of 100 kilopascal polytropically with a polytropic exponent whose value is equal to the specific heat ratio called isentropic expansion. Determine the final temperature and boundary work done during this process. So we know the P1 is 130 kilopascal T1 is 120 degrees Celsius, and in terms of Kelvin it is 393 Kelvin, and V1 is 0.07 meter cube, and it is expanded to a second pressure of 100 kilopascal. And the expansion is isentropic, so PV power gamma is equal to constant, and since it is given as a nitrogen gas, which is a diatomic gas, we know gamma is 1.4. So we have to find the final temperature and the boundary work done. So since PV power gamma is equal to constant, we know P1 V1 power gamma is equal to P2 V2 power gamma. From equation of state we also know P1 V1 is equal to mR T1, so that means P1 V1 by T1 is equal to P2 V2 by T2, because M and R is constant. So if you take constant on one side, we will have PV by T in one side, on the other side. Okay. Now we have to find the final temperature, so that means T2 is what we need to find. We write it as T2 by T1 as P2 V2 by P1 V1. Now we know the pressure, but we don't know the volume, so I want to write the volume ratio as in terms of pressure ratio. So using this expression I can write V2 by V1 is equal to P1 by P2 power 1 by gamma. So now substituting in this equation, T2 by T1 is equal to 364.6 Kelvin. Okay, let's find it. P2 by P1, this can also write as P2 by P1 power 1 minus 1 by gamma. Then we will have totally P2 by P1 is gamma minus 1 by gamma. So we know P2 is 100 kilopascal by 130 kilopascal power 0.4 by 1.4, and T2 is the whole thing multiplied by the T1, so that is 393 into this, and that is found to be 364.6 Kelvin. Now we can find the work done. Work done we have earlier derived that it is P1 V1 minus P2 V2 by gamma minus 1. So here again we don't know the volume, or we know P1 V1 is RT1. From equation of state it can be written as P1 V1 as mRT1. Here we consider, okay, we don't know the value of m also, so either we have to find m or we have to find the value of T2. So from here we can find V2. V2 is V1 into P1 by P2 power 1 by gamma. So that is V1 is 0.07 into P1 by P2 is 130 by 100 power 1 by 1.4. Can you find the value of V2? Yes, 0.084 meters squared per cube. Now we know work done is P1 is 130. I would write the kilopascal 10 power 3 common. So then into V1 is 0.07 minus P2 is 100 kilopascal into 0.084 into 10 power 3 for the kilopascal divided by gamma minus 1, that is 0.4. So we can calculate the work. Yes, 1750 joules. Do you have any questions in the problem? Okay, we can move on to the next one. A mass of 2.4 kg of air at 150 kilopascal and 12 degrees Celsius is contained in a gas-tight frictionless piston cylinder device. The air is now compressed to a final pressure of 600 kilopascal. During the process, heat is transferred from the air such that the temperature inside the cylinder remains constant. Calculate the work input during this process. So it is a mass is given as 2.4 kg, P1 is 150 kilopascal, T1 is 12 degrees Celsius, and that is 285 Kelvin. Now P2 is given as 600 kilopascal, and the temperature remains constant, so it is a isothermal process. We know what done is integral Pradeev E. Here the pressure and volume change with respect to during the process, both will keep changing. But so both will keep changing, so we can find an expression of pressure as a function of volume, right? So we know PV equal to RT. Since T is constant, we know PV is equal to constant, or I will write C. Now volume equal to this constant by pressure. I think it will be something like ln V2 by V1. I will find it. Work done is equal to pressure is equal to constant by volume. Then we will have constant dV by V. So this is constant can be taken outside. We will have dV by V. So this is constant is PV. Integral integral dV by V is ln V over the limits V1 to V2. Yes. So work done can be written as P1 V1 ln V2 by V1. Now we know so now we do not know the value of V, right? V at both the conditions. So that can be found. P1 V1 equal to mR T1. It is given as air. So P1 is 150 into 10 power 3 V1 is equal to so this is capital V1 because we consider mass. It is 2.4 into R is 287 into T1 is 285. So V1 is 2.4 into 287 into 285 divided by 150 into 10 power 3. So the value of V1 can be calculated. Yes, it is 1.308 meters cube. Now we need to know V2 by V1, but we know the pressure relation, right? So we know P1 V1 equal to P2 V2. So V2 by V1 is equal to P1 by P2. That is 150 by 600. So that is 1 by 4. Now we can write work done is equal to P1, which is 150 into 10 power 3 into V1 is 1.308 into ln of 1 by 4. So we can calculate the value of work done. Yes, answer is minus 272 into 10 to the 3 joules. So this is minus 272 kilojoules. The work done we have got as negative because there is a compression work done on the air or the gas, so work is done on the system, so we are getting a negative value for work done. Do you have any questions on this problem? The next problem, we have a well insulated rigid tank that contains 5 kg of a saturated liquid vapor mixture of water at 100 kilopascal. Initially 3/4 of the mass is in liquid phase. An electric resistor is placed in the tank, is connected to a 110 volt source, and a current of 8 ampere flows through the resistor when the switch is turned on. Determine how long it would take to vaporize all the liquid in the tank. Also show the process on the TV diagram with respect to saturation lines. So this is a general TV diagram. You can see on the left. On the left hand side we have a compressed liquid region. So that means when the temperature is low and volume specific volume is low, the water stays at liquid region, and when you start heating up at constant, so these dotted lines represent constant pressure line. Assume you are at this point, and then when you start heating, the temperature will keep rising, and also the volume will also rise. Volume of the liquid also rises, and after reaching the saturation line, so that means at this point, say at for atmospheric pressure, that is 1 bar atmosphere, 1 atmosphere, this temperature is around 0 degrees Celsius, 100 degrees Celsius, after which the liquid will start to become vapor. So there is a phase shift from liquid to vapor, liquid to gas phase, and during this phase shift we will add heat to the system, but this heat will not raise the temperature of the system, but it will only change the phase of the fluid, and that is how this dotted straight line were obtained by changing the state of the system, phase of the system, without raising the temperature. We have increased we have added heat to the fluid, and during this process there is more and more of vapor is formed, and that is why we are having a rise in the specific volume. And after reaching saturated vapor line, so at this point, this is again 100 degrees Celsius, where the entire system is in vapor phase, and beyond this point, after adding further heat to the system, we will see the rise in temperature and also rise in specific volume. So that is why we see around say 45 degree line and not a horizontal line anymore. And so for different pressure there will be different lines like this, and now we are told that there is a container which has a constant volume, and initially it is at 100 kilopascal of water, and initially itself it is having a mixture. So it is a mixture of so total mass is 5 kg, m is equal to 5 kg, and 3/4 of the mass is in liquid phase. So that means you can define state x here. So if the point is here, if the state is here, we will say x is equal to this distance. Say this is x1 and this is x2. We will say this is x1 by x2 by x1 plus x1 x2. So this is like the mass of the fluid in vapor phase divided by total mass of the system. So then that would see if x is equal to 1, that means fully saturated. Sorry, or write saturated vapor. Or x equal to 0 implies it is saturated liquid. So now we have a x of 3/4. So that is 1 minus 3 by 4. That is 1/4 of the total system is total mass of the system is in vapor phase. Now power is given. Power is voltage into current, so that is 110 into 8, and that is 880 watts. And how long it will take? So this is a constant volume process. So, and latent heat of vaporization can be taken as this value, or we can also take it from the table. For simplicity, we will assume that the total mass goes to vapor phase, and we will use only the latent heat of vaporization. So now total mass is 5 kg, and initially mass of steam is 5 by 4, that is 1.25 kg. Initial mass of liquid is, or fluid is, 5 minus 5 by 4, that is 3.75 kg. Now we need to vaporize this mass. So Q is equal to mf1 into hfg. Hfg is generally denotes latent heat of vaporization. So this is 3.75 into 2264 kilojoules. So this is 8490 kilojoules. Now this has to be done by this heat transfer should occur by a power source of 880 watts. So Q is equal to power into time. So time is Q by T, so Q by power. So this is 8490 into 10 power 3 divided by 880 watts. This is 907 seconds. So this is around 2.67 hours. So if you want to represent this in a TV plot, initially it is somewhere at this region, and finally the pressure will also increase. So this is some pressure line P1, so this is another pressure line P2. So this is state 1, and this will be the final state. So this can be said as state 2. This is how we can represent in a TV plot. So later you will also find that this can be found by if you have the steam table with you, you can find the enthalpy at 2 for the 2G. So this is saturated steam, and similarly H1 is H1F plus X1 into HFG at state 1. So for this pressure you can find the HFG from the table and then use X1 and then calculate this. So this is a more accurate way, but for simplicity I have taken like this. Do you have any questions? You can try to solve this problem. I will come back in say 5 minutes. We have an insulated piston cylinder device, contains 5 liters of saturated liquid water at a constant pressure of at a constant pressure of 175 kilopascal, water is stirred by a paddle wheel while a current of 8 ampere flows for 45 minutes through a resistor placed in the water. If one half of the liquid is evaporated during this constant pressure process and the paddle wheel work amounts to 400 kilojoules, determine the voltage of the source. Also show the process on PV diagram with respect to saturation lines. So we are going through a constant pressure process, and initially it was a saturated liquid at the pressure of 175 kilopascal, and the water is stirred. Okay, so first we can draw a PV. First we will see in a TV diagram. So this is the saturation line. Initially we said it was said that it is in a saturated liquid line at a pressure of some 175 kilopascal, and now it is heated at a constant pressure, and the final process is the final state is somewhere inside the saturation dome, and only half of the fluid has become has evaporated. Okay, so that means we can find the enthalpy 1F, or enthalpy 1 is equal to enthalpy 1 fluid, and enthalpy 2 is enthalpy 1 fluid plus x2 into HFG1. Here x2 is 0.5. So our area, this point of interest is 175 megapascal, kilopascal. So that will be here. 175 kilopascal is 0.17 megapascal. So here we can see it is the pressure is given in megapascal. So we have to interpolate the values in between these two, but for some, yeah, we can interpolate that. And now we need to find the value of enthalpy HF, and HFG is enough. So for at 175 kilopascal, we have 160 kilopascal and 180 kilopascal HF and HFG. HF is 475.4 and 490.7. 475.4, 490.7. HFG is 2220.6. and 2210.7. Okay, we also had a Hg value, so that means enthalpy, Hg is enthalpy at the saturated vapor state, and Hfg is the difference between these two. So now you can find for the vapor either as H1F plus Hg minus Hf into X1, right? Or you can calculate H1F plus Hfg into X1. So these both are Hfg is always Hg minus Hf. You can also find in this table, you add these two, you will get this one, and most of the table will not have this value at all. So 475 plus 2220, you will get 2696. Now we want to find the HF and HFG value at 175 kilopascal. So at 175 kilopascal, HF is equal to, we can use a linear relation. So we had y equal to, y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1, right? So from here we can have, we have found a 483.0. And similarly we need HFG also. For others who don't know, I will just explaining. So with a linear line relationship, we can have y equal to y1 plus 2215.64 plus y2 minus y1 into x minus x1 divided by x2 minus x1. So this is how we get the value of y. So now we have these two. H1 is H1F, this is 483.05 kilojoule, and H2 is H1F plus X2 into H2FG, so that is 483.05 plus 0.5 into 2215.65, right? Yes. So calculate the value of H2. kilojoules. So these all are in terms of kilojoule per kg. Now we are given that the device contains around 5 liters, so approximately it will be 5 kg of M is approximately 5 kg. You can also find it in this one at different pressures. So you can see it is around 1054 and 1058 meter cube per kg. So this is, if you convert this, you will get around 1054, around 1000. So we can assume it is 1000. So mass is 5 kg, and now Q is M into H2 minus H1. So that is 5 into H2 is 1590.87 minus 483.05. Can you calculate the value of Q? So this is 5539.15. 5539.15. This is in kilojoules, and we were told that for 45 minutes some resistance, some resistor in for 45 minutes 8 ampere of current flows to a resistor, and also because of paddle work some 400 kilojoule is transferred. So Q is equal to Q paddle plus Q resistor. Now this is 5539.15 is equal to 400 kilojoules plus we know it is voltage into I into T. So voltage into I is 8 into T is given as 45 minutes. So that will be 45 into 60 seconds. So this is 45 into 60, and this entire thing will be in joules. So to convert it to kilojoules, we have by 1000. So we can calculate the voltage. So that is 5539.15 minus 400 into 1000 divided by 8 into 45 into 60. Yes, it is around 238 volts. The next problem, a piston cylinder device contains a steam initially at 1 megapascal, 450 degrees Celsius and 2.5 meter cube. Steam is allowed to cool at constant pressure until it first starts condensing. Show the process on a TV diagram with respect to saturation lines and determine the mass of the steam and final temperature and the amount of heat transfer. So there is a piston cylinder device. and initially P1 is 1 megapascal and T1 is 450 degrees Celsius and volume is 2.5 meter cube. It is allowed to cool at constant pressure until first start condensing. So this state should be a supersaturated steam. We can also check it in the steam table. At 1 megapascal we can find the saturated temperature. At 1 megapascal the boiling point of water is 179.7 degrees Celsius, but our system was at 450 degrees Celsius, so that means it is a superheated steam. And we'll represent that in a TV diagram. So we are somewhere at this point at 1 megapascal and it is cooled at constant pressure, and so this is a constant pressure line. This is state 1 and it is allowed to cool at a constant pressure until it first start condensing. So it will start to condense at this point. So this is point 2. To find the mass of steam we want the specific volume, and to find the final temperature is what we saw just now. So it is 179.7 degrees Celsius. So T2 is 179.9 degrees Celsius and the amount of heat transfer can be computed. Okay, so for the amount of heat transfer we would need the enthalpy at both the states 1 and 2, and for mass of steam we want the mass at first state. So to find the such specific volume, here you find only the specific volume of the fluid and the steam. To find the properties of the superheated steam there will be another set of tables. For 1 megapascal here it is, and temperature is on this axis. So we are interested at 450 degrees Celsius and the specific volume is given as 0.3305. So that is specific volume is 0.3305 meter cube per kg, and the enthalpy is 3371.3. From this V1 is 2.5 meter cube, so mass is 2.5 divided by 0.3305. Can you compute the mass? 7.56 kg. The final temperature we have found and the amount of heat transfer. So H1 is already known. H2, to calculate H2 we need to go to the saturated table. So it is 1 megapascal. 1 megapascal the Hg is 2777.1 equal to 2777.1 kilojoule per kg. So heat transfer is m into H2 minus H1. M is 7.656 H2 is 277, sorry, H2 7.1 minus 337113. Minus 4.5 kilojoules. We have got negative because the final enthalpy is lesser than initial enthalpy. So this is the amount of heat this transfer. Do you have any questions in this problem? Okay, so there are no questions. I will move on to the next problem. These problems are from the previous week syllabus, where I didn't have time to solve, so we can solve it now. A car is accelerated from rest to 85 km/h in 10 seconds. Would the energy transfer to the car be different if it were accelerated to the same speed in 5 seconds? Can you guess if the energy transfer will be different or same? So energy transfer to the car is the kinetic energy, and that is half mv square. Initially it is rest, it is at rest, so we will have mv2 square, right? Finally, this is final speed, and there is no here there is no term of speed or term of time. Like if it is a 10 or 5, we would have used the same expression with the same values. Only thing, the rate of energy transfer or the power at which it is transferred will vary, but the total energy that transfer will be the same. And we can also calculate that 85 km/h is 85.3.6 meter per second. So this is okay. Anyway, the mass of the car is not given, so we can do this. So the answer will be it will be the same. Next problem: lifting a weight to a height of 20 meter takes 20 seconds for one crane and 10 seconds for another. Is there any difference in the amount of work done on the weight by each crane? Again, the amount of work done is same, but the rate at which the work done is different. Then Determine the energy required to accelerate an 800 kg car from rest to 100 km per hour on a level road. So now we can calculate kinetic energy is equal to half mv square, and that is half into m is 800 kg, and final velocity is 100 km per hour, and to convert in meter per second we will have 100 by 3.6 the whole square. Can you complete this? Okay, 309 kilojoules. I hope you have calculated and not just give me this value. Determine the energy required to accelerate a 1300 kg car from 10 to 60 km per hour on an uphill road with a vertical rise of 40 meters. So now the total energy is the summation of the kinetic energy plus the potential energy, and for kinetic energy it is half mv1 square, sorry, v2 square minus v1 square, plus the potential energy is mgh. We can rewrite this as it is a 1300 kg car by 2 into 60 km per hour is 60 by 3.6 square minus 10 by 3.6 square plus 1300 into 9.81 into h is 40. So can you compute the total energy? Yes, 6086 kilojoules. Next problem, determine the torque applied to the shaft of a car that transmits 40 HP and rotates at the rate of 3000 rpm. So this is power is equal to torque into omega. Power is 450 HP. To convert this into kilowatt, we have 1 kilowatt is 0.746 HP. Sorry, so 1 HP is 1 HP is equal to 746 watts. So this is 450 into 746 is equal to torque into omega. Torque is T, and omega, to convert the rpm in radians per second, we have 300 into 2 pi by 60. So the value of torque can be calculated. 1069 Newton meter. Next, determine the work required to deflect a linear spring with a spring constant of 70 kN per meter by 20 cm from its rest position. So F1 is 0 newtons, F2 is 70 kilonewton into 0.2 meters, right? So this is 14 kilonewtons. So that means force and distance we have initially at 0 distance and 0 Newton force, and then it linearly increased to 14 kilonewtons, and the distance is 0.2 meters. Now the work done is the force into distance, or in the case where the force is varying, we have to consider the area under this curve. And to find the area under this curve, we can take it as a area under the rectangle, and that is half into work done is half into 14 kilonewtons into the distance 0.2. So work done can be completed. Yeah, 1400 joules. Next, engine of a 1500 kg automobile has a power rating of 75 kilowatt. The time required to accelerate this car from the rest to a speed of 100 km per hour at full power on a level road is what we have to find. Mass is 1500 kg and power is 75 kilowatt. Final speed V2 is 100 kilometer per hour. Now the kinetic energy at the final state 2 is half mv square, that is half into 1500 into v square is 100 by 3.6 the whole square, and you compute the value of kinetic energy. Is 79 kilojoules. 579 kilojoules. Okay. Now power is energy spent over time. So that is 75 into 10 power 3 is equal to 579 into 10 power 3 divided by time, and time is 579 by 75. Can you calculate the value of time? Okay, 7.72 seconds. Is this value realistic? In reality, do you think we will get 7.72 seconds or more or less? You can type in what you feel. Or you can also unmute and answer. Okay, in reality it will be more than this. Say the time will be around 10 to 15 seconds. And why it is so is the engine will not be able to deliver 75 kilowatt at all times. So there will be something like a power output of the engine to the speed of the engine. And say this is like 1000 rpm and somewhere it is 6000 rpm and so on, and this is the maximum power will be something like this, and maybe at 5000 rpm it can deliver a maximum power of say 75 kilowatt. So at all other times it cannot deliver 75 kilowatt. So because of this, realistically it cannot be 7.72 seconds. It has to be always it will be always less than this value. Do you have any questions, or we can move on to the next problem? Moving on. A sky lift has a one-way length of 1 kilometer and a vertical rise of 200 meters. The chair are spaced 20 meters apart, and each chair can seat 3 people. The lift is operating a steady speed of 10 km per hour, neglecting friction and air drag, and assuming that the average mass of each loaded chair is 250 kg. Determine the power required to operate this sky lift. Also estimate the power required to accelerate the sky lift in 5 seconds to its operating speed when it is first moved on. So sky lift is something from a base station to is connected to the top station, and if you see from the top, there will be chairs hanging on this, and they say the one-way length is say 1 kilometer, and for every distance between each chair is 20 meters. So there will be in total 5 here and 5 in the reverse direction. So totally 10 chairs will be there. Or considering one way, we will have 5 into 250 kg that is getting lifted, and this is raised to a height of 200 meters. So total is 1250 kg, and h is 200 meters, and velocity is 10 kilometer per hour. So since it is 10 kilometer per hour, for every hour it will be for if it is taking 1 kilometer, it will deliver the mass of 1250 kgs. So for every hour it will deliver 10 times of this mass. And to calculate the potential energy that it is taking, we will have mgh, so that is 1250 into, I would approximate this to 10 meter per second, into h is 200 meters. So this is 2.5 megajoules of energy. And this is delivered in rate of so 10 kilometers in 1 hour or 3600 seconds. Then 1 kilometer will be done in 3600 into 10 by 10 in 360 seconds. So for every kilometer for the cable to travel, it will take 360 seconds. This energy has to be done in 360 seconds. So power is steady, that is considering only the potential energy delivery. We will have 2.5 by 360 megawatts. So this is 6.9 kilowatt. And the kinetic energy is again half mv square, and that is half into mass of 1250 into v is 10 by 3.6 the whole square. So this is 4822 joules, and this has to be done in 5 seconds. So power for kinetic energy to impart kinetic energy in 5 seconds will be 4822 by 5, and that is 964 watts. So during starting, is 964 plus 6900 watts, and that is roughly 7864 watts. Okay, I hope this problem is clear. Thank you for participating. We will see you in the next class. Thank you.